All right, here we go again. Chemistry 3202 course overview. Review. Here we go. All right, what we're going to look at here in this little clip is some more work on calorimetry. So the sequel, Calorimetry Revisited. We've already talked a little bit about calorimetry, but we're going to take it now a step further here and do some different types of calculations that are involved in calorimetry. So here we go. Okay, here's some background information on this if you want to consult your textbook, and there's a few practice problems here that you can give a try, and if you can't get these or you need some help, then make sure you fire these off at your online tutor, or you fire something off in the discussion link so I can try and get back to you. All right, so remember now, last time we were talking about calorimetry, we were just basically talking about some simple calorimetry, and we did a little bit of bomb calorimetry as well. And we're going to take this a little bit further and look at some of the things that go along with this calorimetry. So here we go. Okay, here's the outcomes for this lesson. And the very first thing we want to refresh or review in our mind here is, what is calorimetry doing? All right, so calorimetry is simply a process by which we can measure the amount of energy change of some type of process that we're studying. Now, in the last example we were doing some simple calorimetry where we were dropping a piece of aluminum that was very hot in the water, and it would release its energy to the water, and we could calculate the energy change. Therefore, we could calculate Q, or the amount of energy that was in the water, and or the amount of energy that was in the aluminum. In this case, what we're doing, we're still basing it on the idea of the first law of thermodynamics, and we're saying the energy of the system is equal to the energy that was absorbed or released by the surroundings, so vice versa. So if the system gained energy, the surroundings would have lost energy. And likewise, if the system lost energy, then that energy would have been gained by the surroundings. So remember now, this is the first law of thermodynamics. And let me just jot that there. That's the first law. Not the first call, the first law. There we go. And calorimetry, of course, is based on that. That's the premise behind it. We said there's two types of calorimetry here. The simple one that we generally use in the lab, and you guys should have done a lab on this by now. You should have done probably a couple labs. And what we're going to do is talk about the lab and see where we could improve on this calorimetry calculation that we're going to do. So in this case, with simple calorimetry, it's constant pressure, which means if there's any gases or anything that are being produced, the gases would be vented, right? There's cracks in the lid of your styrofoam cup, and where you push the thermometer down or the stirring rod, the gases can escape there. So essentially, with simple calorimetry, it's atmospheric pressure. Whatever the pressure is outside the cup, it's going to be the same thing as the inside. So pressure is not allowed to build up. The other type of calorimetry we looked at, of course, was the bomb calorimetry, and this is a case where we had constant volume calorimetry, and this is where everything is encased in a very rigid bomb container that if a reaction took place, if there's any gases produced and heat and whatnot, then the gases wouldn't get a chance to expand. They would have to build up within the calorimeter because the volume's constant. Therefore, the pressure would start to rise. And it gets a bit complicated because when gases expand, they're losing energy, all right? And in the bomb calorimeter case, they're not allowed to expand, so that energy is kept within the bomb. So it's a little more precise, a little more accurate. And of course, it's the bomb calorimeter is going to be used for specific applications like measuring the heat of combustion of, say, a sample of gasoline, or the heat of combustion of a peanut, or something that's going to be burned and producing gases and whatnot. Typically, a simple calorimeter would be the ones that involve aqueous solutions, remember? Because in this case, the styrofoam cup wouldn't be able to withstand large temperature changes, wouldn't be able to withstand extreme pressure buildup, right? The styrofoam would rupture. And not only that, you wouldn't combust something in a styrofoam cup because the styrofoam cup would catch on fire and burn itself, and that wouldn't be any good. And also some solvents like gasoline or naphtha or whatever type of material you're trying to burn could possibly dissolve the styrofoam itself. So styrofoam cup, simple calorimetry, it's going to be based on generally aqueous solutions, and that makes it easy for us because generally we would assume that the calorimeter surroundings, the water, is going to be our surroundings. In this case down here, the calorimeter constant would be calculated and it would have a specific number. And it has no mass in this particular reaction here. In this particular constant, sorry. So in this case, the specific heat would be kilojoules degrees Celsius. So if I wanted to calculate the energy absorbed by the calorimeter, we would not include the mass. Okay? But in the case up above, we would include the mass because it's the mass of the water, which would be our surroundings. All right? So a big difference here with simple calorimetry and bomb calorimetry. So let's have a look at some of the assumptions that we're going to make. So of course this one is the bomb calorimeter, and this guy up here is the simple or constant pressure calorimeter. Here we go. Okay, so we're doing this experiment in the lab. All right, we're doing the, we're dissolving some ammonium nitrate in water to see how much energy gets absorbed. Another lab we do is we like to dissolve sodium hydroxide in water to see how much energy it releases. So we'd have to come up with some assumptions here that we're going to base our calculations on, and we say, well, we're not in a perfect world. What we do in the lab is not an ideal world. There's issues and concerns that come up with this very experimental procedure that we're going to do. So we want to be able to acknowledge that, yeah, we know there's some downfalls and pitfalls to this procedure, but we're going to keep that in mind so that when we do our calculations at the end, we say, yeah, okay, we're going to be pretty close to the actual result. We're off a little bit because of these reasons. And here's the reasons why calorimetry could be, you could get results that are somewhat different than what you expect. Not a lot different, just slightly different, so like a % discrepancy. The very first thing we're looking at here is the idea that we're assuming that the calorimeter is a universe within itself and that it's completely isolated from the outside world. And we're saying then that no energy can get into the styrofoam cup, but at the same time that no energy can get out of the styrofoam cup. So we're assuming that the styrofoam cup is a universe within itself, and that could be flawed because in the real world we know that energy can go in and out of the styrofoam cup because we've all had a hot cup of coffee or hot chocolate or something like that. If you leave it long enough, even though it might be in a styrofoam cup, give it time and eventually the hot coffee or hot chocolate would eventually cool off, and it just takes time for it to cool off. But it will cool off because it's losing energy outside the styrofoam cup. So therefore, the styrofoam cup, our simple calorimeter, is not so much an isolated system as we like to think it is. All right. So when we do our calculations, we have to realize that, yeah, energy is being lost outside the styrofoam cup, but we're going to assume that no, none is. Right. We're going through this with blinders on, and we're saying that no energy is going to be exchanged to the outside world from the styrofoam cup. So the styrofoam cup is a universe within itself. So that's going to create a little bit of discrepancy in our results. Okay, the second thing is that we're saying the first law of thermodynamics is absolutely 100% true, and that energy is completely transferred from the system to the surrounding. So in other words, what we're saying is that our surroundings, I got a mistake there, look at that. That's supposed to be system, not system. The system, that's supposed to be surrounding. Okay, so we're going to assume then that any energy that's given off by our system is going to be absorbed by the water, and only the water. When we do our calculations for simple calorimetry, we would say it's Q equals mc delta T, the mass of water, the specific heat of the water. And we're going to assume that the thermometer doesn't absorb any energy, and then the stirring rod doesn't absorb any energy, and that the styrofoam doesn't absorb any energy. But we know full well that the whole principle on how a thermometer works is that it's absorbing energy to make the alcohol molecules vibrate quickly, and then they start to take up more space and they start moving up and squeezing up through the tube of the thermometer. So we know very well that that's how the thermometer works. But we're going to assume that that energy doesn't exist. It's so small that it's insignificant. It's not going to really affect the overall result. But we know that it's there. All right. So we choose to ignore it, but we have to keep in mind that that's how it works. That's energy is being absorbed by other things too. We're also going to make the assumption that the calorimeter itself is considered negligible in terms of the amount of energy it would absorb or release. And we're saying that, okay, just stop for a second here now. Styrofoam is matter. All matter is made of molecules, and all molecules get excited when they get heated, and they start absorbing energy and vibrating quickly. Some substances absorb more energy than others. We know that from our study of different heat capacities, like copper absorbs about 0.3 joules per gram, whereas something like aluminum absorbs a lot more energy. It can absorb a lot more energy, 0.9 joules per gram. So different substances absorb different amounts of energy. So why would it be any different than styrofoam? Styrofoam is made of matter molecules. The styrofoam is going to start to vibrate. It's going to get warmer. If you have a hot cup of coffee in your hand with a styrofoam cup, the styrofoam does feel warm, right? So it does absorb a little bit of energy. So we're going to assume then that the styrofoam is, the amount of energy that a styrofoam cup absorbs is going to be near zero because it has such a very tiny heat capacity. So the heat capacity of styrofoam is so small that the amount of energy it absorbs is going to be negligible when it comes to our calculation up here. All right? Is it zero? No, it's not zero, but it's very tiny, so we're going to assume it's zero. All right? You see where we can start to get sources of error building here? And the fact that our answer is going to be off. You know, here's three different little things where our answer is going to be slightly different than what we expect it to be. And the last thing here is lots of times we do calculations in which the system actually becomes part of the solution. And you guys should have done a lab on that. So something like the dissolving of, say, sodium hydroxide. When sodium hydroxide is placed in water, it actually dissociates. So it doesn't exist as sodium hydroxide. It actually exists as sodium ions dissolved in the water and hydroxide ions dissolved in the water. So if I took 2 grams of this stuff and dissolved it in, say, a volume of 100 milliliters of water, the water is going to have a mass of 100 grams, and now the sodium hydroxide has dissociated into the water. So the overall solution on this side would have a mass of really 102 grams. That would be my solution mass. So what we're saying then is that in this case, instead of just looking at the mass of water as my surroundings, now because the sodium hydroxide has moved into the solution, we would consider the mass of the solution here to be 102 grams. All right, fine and dandy. It's somewhat like an open system where the mass of the surroundings has increased as a result of the process. Not a problem. We can accommodate that in our calculation because in our calculation Q equals mc delta T, instead of using 100 grams of water, we're going to say we got 102 grams of solution. Not a problem. However, the issue comes up here is where we say, well, we now have a new substance. We have a solution in which case it's going to absorb more or less energy than it could before when it was just pure water. But we're going to ignore that, and we're going to say that because we're only dealing with small amounts of solute, the change in the concentration or the density is going to be negligible. And because it's negligible, we're simply going to assume that the concentration, or sorry, the heat capacity of the solution is approximately the same as the heat capacity of pure water. And we're going to look at this and say that our heat capacity is 4.184 joules per gram degree Celsius. It's the heat capacity of pure water, knowing full well that we've got other materials there other than water. We don't have pure water, but yet we're going to assume we do. You know, it's kind of leading us into areas whereby we say, you know, how accurate are our results going to be? Well, we're actually going to get some nice results here. We get some results that are pretty close to what we expect, but they're going to be off a little bit. And these would be the reasons why they would be off a little bit. Not to mention that little Johnny there just spilt some, and the other fellow never started the clock in time, or he stopped it too late, or you weren't measuring the actual results with your thermometer accurately. Like, those are human errors, so they're going to come into play as well. But these are things that, these assumptions that we do in our calculations, these are things that that you can't really control because we're assuming these in order to make the calculations easier. Okay, so here we go. Here's a few examples then of simple calorimetry. Okay, let me just go back a second here and look at our diagrams. Now, in the case of simple calorimetry, these are all assumptions based on the solution that's being produced here and all that. In the case of bomb calorimetry is a little more accurate. Because in this particular example, we're saying that the C is going to be the sea of pure water. Okay? Down here, and this is going to be based on the 4.184 joules per gram degree Celsius. Over here, we've taken all that out of the equation. We've taken, in the bomb calorimetry, we've included the thermometer, we've included the stirring rod, we've included all of these items here that are going to be absorbing energy. And we include all that in our calculation so that we say C of the calorimeter is going to be a specific number, say 1.5 kilojoules degrees Celsius, which takes into account all of the things mixed together. We're not saying that we're just measuring the water outside here. We're measuring everything, and that's been taken into account. So this is going to minimize some of the errors or the assumption that's associated with using this guy as a solution, but yet it's pure water. We ignore that the thermometer exists. We ignore that the stirring rod exists. So the bomb calorimetry is going to be a little more precise, a little more accurate than, say, simple calorimetry. Okay, so here we go. Here's an example where we could possibly do this in the lab, and this one's saying we're going to take some hydrochloric acid. They give us the volume and concentration, and we're going to react it or mix it with sodium hydroxide. So what we're going to see here is going to be a neutralization reaction where we're going to neutralize an acid with a base. And what we're going to look at here is we have to decide, what is our system and our surroundings. And our system is going to be the process of neutralization of the acid with the base. Now, when we read further on here, we're saying the highest temperature reached after mixing was 26 degrees Celsius. We want to calculate the molar heat of reaction with respect to the sodium hydroxide. So in this case, our system, the calculations are going to be based on, everything we're going to do is we're going to say what's happening with respect to the sodium hydroxide. If they wanted us to refer to the hydrochloric acid, then they would have said calculate the molar heat of reaction with respect to the hydrochloric acid. So in this case, everything we're going to talk about in terms of the system is going to be with respect to the sodium hydroxide, the concentration, the volume of the sodium hydroxide, and likewise we want to figure out the heat of reaction with respect to the sodium hydroxide. Okay? Now our surroundings in this particular example, we're saying, well, we're mixing this together in a styrofoam cup, so our surroundings is essentially going to be the water, but more importantly, it's going to be the solution. Okay? And what we're going to say then is that the mass of the water is 100 grams because the density of water is 100 grams. Now we've got to look and see what's going on here. What we're going to do here is we're going to take some sodium hydroxide and react it with hydrochloric acid. So remember what we said about solutions. We're assuming that in terms of calculating its mass, we're going to assume that everything is pure water. So really, rather than having 50 milliliters of sodium hydroxide and 50 milliliters of hydrochloric acid, in terms of the energy that it's going to absorb, we're going to assume 100 milliliters of water, knowing full well that it's not pure water that we have, but we're just trying to simplify our calculations. We know our initial temperature of the two mixtures, it's 22.5, and we know our final temperature here of the solution mixture, it's 26. So energy was being absorbed. This was getting hot. All right, we're going to assume then that the surroundings is not sodium hydroxide or hydrochloric acid. It's simply 100 milliliters of water. All right, so we're going to assume the specific heat capacity of water. Okay, can we do this? Well, when we try and do these calculations, we're looking at this and we're saying, if I want to get I like working these backwards. If I want to get the heat of reaction here, I need to know the Q of the system, and I need to know the number of moles of sodium hydroxide, because that's the one I'm doing the calculation for. Now the number of moles of sodium hydroxide is easy enough, because C equals N equals C times V for the sodium hydroxide, so that's easy enough. I know C for sodium hydroxide. I know V. So I can calculate the number of moles. That's done. Now, if I can calculate the energy that was absorbed or released by the sodium hydroxide as it was reacting, then I'm in business. And I'm saying, well, I don't know anything offhand, but I do know the first law of thermodynamics. I do know that the Q of the system is equal to any energy absorbed or released by the surroundings. So can I calculate the energy of my surroundings? And the answer to that is absolutely. Because I know the mass, I know the specific heat, I'm using pure water, and I know the change in temperature. So this question's easy enough. So I'll plug my values in for the first equation here, Q equals MC delta T. Okay, so 100 grams of solution times 4.184, assuming pure water, times the TF minus TI, so 26 minus 22.5. And what I get here is a positive 1464.4 joules of energy absorbed by this solution. That energy that was absorbed by the solution must have been released by the surroundings. So I'm saying Q of the system equals minus Q of the surroundings. So the surrounding, therefore, the system released 1464.4 joules. Now you notice what I've done here? I've changed my joules to kilojoules because I'm setting it up in order to calculate delta H. Delta H is generally given in units of kilojoules per mole, remember? So I simply divided this by 1,000 in order to convert that to kilojoules. Okay? And therefore now I can calculate the number of moles of sodium hydroxide, N equals C times V. Don't forget to change your volume to liters. Now you might say, well, why didn't you use 100 mils? Because that's how much we have, 100 mils of solution. But remember, I'm not talking about the solution here now. I'm asking you how many moles of sodium hydroxide, because that's what we want to calculate the energy for. How much energy was released per mole of sodium hydroxide? So when I do this, my volume of sodium hydroxide is only 50 milliliters, 0.0500 liters. All right, it's not 100 because I never put in 100 mils of sodium hydroxide. I only put in 50 mils. Okay, so be careful with that. That's a mistake some people make there. So we calculate that, and it works out to be 0.0250 moles of sodium hydroxide. And now, of course, we put our question, our answers, we put our numbers in here. Q of the system divided by the number of moles of sodium hydroxide. And therefore, keep your negative sign, right? Make sure you carry down your negative sign, because we're saying that as the sodium hydroxide is neutralized, energy is going to be released. We know that because the system got warmer. The surroundings got warmer. And therefore, we put our values in, and it works out to be a negative 58.576. And don't forget now the units, kilojoules per mole, and the fact that it's a negative, so this means that sodium hydroxide releases that much energy. Now, significant digits, I'm looking up here and I'm seeing that the concentration is only 2 significant digits. The 0 doesn't count. The volume is 3 significant digits. Okay, the temperature is 1 decimal place. All right, I'm doing a bunch of multiplication, division. My final answer should only have 2 significant digits, so I have to round this to 59. Okay, so that's got to be 59 kilojoules per mole at 58.6. 2 significant digits. Sig figs. Okay, there we go. All right, let's try another one. Okay, here's another one. This one's using a bomb calorimeter, and this time we're taking 1.23 grams of ethine. All right, that's what we use. That's acetylene, like an acetylene torch, lots of heat. Undergoes complete combustion in an oxygen bomb calorimeter. All right, so this is a bomb calorimeter where oxygen is constantly being supplied. So however much oxygen is required as the acetylene burns, the oxygen is not going to be a contributing, it's not going to be a limiting reagent. The oxygen is going to be in excess, so this acetylene can take as much oxygen as it needs. And what we want to do here is we want to figure out the enthalpy of combustion for acetylene. We want to figure out how much energy is going to be released or absorbed as acetylene is burned, and we got the exact mass of acetylene here. It's 1.23 grams. We know the temperature change and we know the heat capacity of the bomb calorimeter. We want to calculate the molar heat of combustion. So here we go. Once again, we have to define what our system is and what our surroundings is going to be. In this case, the system is the combustion reaction. The surroundings this time is going to be the entire calorimeter. So you notice that when we've done bomb calorimetry, we're not making any assumptions about the solution or anything like that, right? We're taking the entire thing of the bomb, everything, and giving it a specific heat capacity, or in this case, a heat capacity. So it takes away any assumptions. And we know the temperature change of the calorimeter. It says it was an increase of 9.5 degrees Celsius. Okay, so it's an increase of 9.5. So therefore it went up by plus 9.5 degrees. And what do we know about the S-ion? Well, we know the mass of the S-ion. It's 1.23 grams. And we know we want to calculate the heat of combustion, and that's all we know. So we're looking at this and saying, well, we don't have a whole lot of information. But again, let's work it backwards. We want to calculate. I love working it backwards because it's a problem-solving strategy and say, okay, what is it I want to do, and let's see how I can get to that final point. So in this particular example, we're saying, well, you want to calculate heat of combustion. Well, in order to figure out the heat of combustion, I need to know how much energy is going to be released, and I need to know how many moles of the substance I'm going to combust. All right. Can we calculate the number of moles of acetylene? The answer to that is not a problem because we know the mass. So N equals mass over molar mass for acetylene. Okay, not a problem. We can do that. So N is figured out. The other thing would be, well, can we figure out the Q of the system? How much energy was released by the acetylene? And the answer to that is we rely on the first law. So we're saying, yeah, no sweat. If we can figure out how much energy was absorbed by the calorimeter or the surroundings, then we should be able to say that that energy was given up by the system. And the question would be then, can we calculate Q of the surroundings? And we say, yeah, absolutely. The surroundings is the calorimeter, so Q equals C cal delta T, and easy enough. All right, we put our values in, and here we go. Okay, so it's going to be 6.49 kilojoules per mole times the plus 9.5 degrees Celsius, and what we're going to get here is a plus 61.655 kilojoules. We say that that energy was released, right? So the surroundings absorbed energy. The system therefore must have released the same amount of energy. We can calculate our number of moles of acetylene. N equals mass over molar mass. Now, the molar mass of acetylene, 2 times carbon, 2 times hydrogen, it works out to be 26.04, right, from our periodic table. And lo and behold, it's 0.04723 moles. And then we plug our values in for our delta H. Now, we got to remember now that delta H is in units of kilojoules per mole. We're in business here because the specific heat, or the heat capacity, sorry, is in kilojoules per mole. So we're in business. We didn't have to do any conversion. And when we plug it in, we get 1305.4. Now the question is, how many significant digits do I keep here? And I would keep, my mass is 3, my temperature has 2 decimal places, it's 3, my specific heat capacity is 3. I'm doing multiplication, division, so my final answer should have 3 significant digits. So what do I keep? Okay, my final answer would be a negative 1310. Now you might say, well, isn't that 4 significant digits? No. The 0 is not significant because there's no decimal place. Another way I could report this is by saying it's a negative 1.31 times 10 to the 3 kilojoules. Or I could change it again and I could say it's a negative 1.31 megajoules. Mega means 1,000 kilojoules. So you can leave it however you want. But anyways, 2 significant digits. So there we go. Okay, here's another one. This one says in order to calibrate a bomb calorimeter. Now what they mean by calibrate, it means to be able to figure out how much energy the entire calorimeter is absorbing. So we do an experiment to check it out to make sure it's working properly and it's absorbing the energy it's supposed to. And then the value we get for the specific heat capacity of the bomb calorimeter is the value that we're used for our experiments. So we try to make it and measure it to be accurate. So we're calibrating it. all right, seeing how much it's going to absorb. So we're going to take 3 2.5 gram samples of benzene. Now we're not going to take 7.5 grams of benzene and burn it all at once. What this means is that we're doing it 3 times. So each time we do it, we're going to try, just like we did with titration curves and titration experiments, you do multiple experiments and then you average the 3 results you get. So we're simply going to do the experiment 3 times, and each time we take an accurate mass of 2.5 grams of benzene, and we're going to burn it in the bomb calorimeter. And it says the average temperature change was plus 4.23. We know the molar heat of combustion of benzene. We can get that from tables in the back of our book, remember, heats of combustions. We want to figure out the heat capacity of the bomb calorimeter. Okay. So once again, calorimetry. So our system is going to be the benzene, the combustion of benzene. The surroundings is going to be our calorimeter. What do we know about benzene? Well, we know how much we're burning. It's 2.5 grams. We're going to do it 3 different trials. What else do we know about benzene? Well, we know how much energy benzene releases per mole. It's negative 726 kilojoules per mole. That's the heat of combustion of benzene. What do we know about the surroundings? Well, we know the change in temperature of the calorimeter. It went up by 4.23. What else do we know about the calorimeter? Nothing. That's what we want to figure out. What is the heat capacity of the calorimeter? Okay, so once again, let's work it backwards, and we'll say, well, if I want to figure out the heat capacity of the calorimeter, we know that generally Qcal equals Ccal delta T. So I'm simply going to divide both sides by delta T in order to figure out my heat capacity of the calorimeter. So we can say, what do we know and what do we need to find? Well, we know the change in temperature. We just don't know the amount of heat energy absorbed by the calorimeter. But we say, yeah, that's not a problem. First law is on our side. So we're saying that any heat that was absorbed by the calorimeter must have been released by the reaction or the combustion of the benzene, our system. And we can say, well, can we calculate the heat that was released by our system? And the answer to that is, well, we know delta H, and we know the heat of combustion. So we can say we know the heat of combustion. Can we calculate the number of moles of benzene? Absolutely we can, because we know the mass. So N equals mass over molar mass for benzene. Let's plug our values in. Okay, it's 2.5 grams. The molar mass of benzene, 6 times carbon, 6 times hydrogen, works out to be 78.12. We figure out our number of moles here. 0.0320 moles of benzene. We'll plug that in our next equation, Q equals N delta H. All right, so 0.0320 moles of benzene times negative 726 kilojoules per mole. And what do we get? We get a negative 2323 kilojoules. So this much energy was released as the benzene burned. The energy that was released by the benzene was ultimately absorbed by the calorimeter, and we keep this as kilojoules because a calorimeter usually absorbs a lot of energy because there's a big bomb, there's lots of water, there's a thermometer. It's a big device, and there's lots going on there. There's lots of energy absorbed. So the energy that the calorimeter absorbs is generally reported as kilojoules. Okay, and therefore now we can calculate the heat capacity of our bomb calorimeter. And it's simply going to be plus 2323 kilojoules divided by a temperature increase of 4.23. And remember, heat capacities are always positive. If you end up getting a negative value here for your final answer, you probably forgot to do the first law. Or you probably forgot to carry the negative sign. All right, but we know full well that heat capacities are always going to be positive because everything absorbs energy. And it works out to be 5.49 kilojoules degrees Celsius. There we go. Okay, last one. And this is one of these that gets a little tricky here, and you got to really be careful about what you're doing with this one. In this particular example, what we're going to do is we're going to take a piece of magnesium, and we're going to drop it in a sample of hydrochloric acid in a styrofoam cup, And you got to be careful with this guy because as soon as you drop it in, you're going to get some hydrogen gas being produced. It's going to start bubbling, and you got to be very careful that you don't spill the hydrochloric acid. And you got your goggles on, and you know it's going to start very, very quickly. So you got to be ready to time and take measurements and recordings. But what we want to do is we want to figure out the heat of reaction for the reaction of magnesium with hydrochloric acid. So let's define the details. Okay, we're using a simple coffee cup calorimeter. So as soon as you see a simple calorimeter, we're going to assume that water is the surroundings. All right, we're going to react 0.5 grams of magnesium with 100 mils of hydrochloric acid, and we know the concentration of hydrochloric acid. The initial temperature was 20.4. After neutralization, the highest recorded temperature is 40.7. All right, now we're going to do this with respect to the magnesium. Because we have large amounts of hydrochloric acid, the hydrochloric acid is going to be in excess. The magnesium is a small, tiny amount. Now you can actually do the calculation to figure it out, but the magnesium is going to be the limiting reagent. So that's the one that's going to control how much energy we're going to get. At the end of this experiment, all the magnesium will be used up. We will still have some hydrochloric acid remaining in the styrofoam cup. So the magnesium is the substance that's going to control how much energy we're going to get. So the system, therefore, is going to be the reaction with respect to the magnesium, okay, not to hydrochloric acid. Hydrochloric acid is in excess. Okay, so we're going to do the heat of reaction with respect to the limiting reagent, which is going to be our magnesium. What else do we know? Well, we're assuming simple calorimetry. So we're going to assume that water is the surrounding. So we're going to assume that the solution now, because the magnesium, as it chemically reacts with the hydrochloric acid, it's producing magnesium chloride AQ. So this excess, this magnesium that was put in here, the 0.5 grams, actually becomes part of the solution. All right? The magnesium ions now are going to be floating around in the solution, and therefore it's going to add to the mass. So in this particular example then, the mass of the solution is really going to be 100 grams of the water. We know it's really hydrochloric acid, but we're going to assume it's water. So it's 100 grams of hydrochloric acid plus the 0.5 grams of the magnesium, which means now we've got 100.5 grams of solution. We know the initial and final temperature, and we're going to assume that we have pure water. Even though we know we have a solution, we're going to assume pure water. Okay, can we do this? The answer is, well, I want to find delta H of this reaction with respect to the magnesium. So it's going to be Q of the reaction, the amount of energy that was given off, divided by the number of moles of magnesium. We can easily calculate the number of moles of magnesium. It's mass over molar mass for magnesium. Can we figure out Q of the reaction? Well, we do our first law. We say that any of the energy that was released or absorbed by the water came from or was given to the reaction. The question is, can we calculate the heat that was absorbed by the water? And the answer is absolutely. We're saying it's mc delta T, but remember now, the mass is going to be the mass of the solution, but yet we still assume we've got pure water. You see where we're going with this, right? We give on one side and we take on another. So we're assuming pure water, so we use the specific heat of pure water, and we know the temperature change, TF minus TI, so 40.7 minus 20.4. And we get this large number. There's a significant amount of energy released here in this reaction. It's a very exothermic reaction, and we know that because the water absorbed a considerable amount of energy. It's a plus value. All right, so we're saying that that energy was released by the reaction. So it's going to be a negative value there. And remember now, we have to set ourselves up here. Because the specific heat of water was joules per gram degree Celsius, our answer works out to be joules. But when we calculate delta H, we really want it to be in terms of kilojoules. So I'm going to divide that by 1,000 to turn that to kilojoules. So that works out to be negative 8.536 kilojoules released during this reaction. We figure out our number of moles here, mass over molar mass, and the molar mass of Magnesium is 24.31, right from the periodic table. And this works out to be 0.0260, sorry, 0.0206 moles right there of magnesium. And then we plug our values in for the reaction and the number of moles here, and we get a negative 414.4. Now again, significant digits here. Well, the mass of the magnesium is 2 significant digits, or 2 digits of measurement. Our temperature has 1 decimal place here. Concentration is 3. But, you know, we never use the hydrochloric acid in our calculation, so these significant digits really don't count. What we're looking at is 2 significant digits. So my final answer down here should really be a negative 410 kilojoules per mole. And again, the 0 is not significant because there's no decimal place. Or if we wanted to write this in scientific notation, we could write it as a negative 4.1 times 10 to the 2 kilojoules per mole. That's how much energy is released per mole of magnesium in this reaction. Okay. Okay, one more thing that we're going to look at is the core lab for Chemistry 3202 would have you do something like this, where you, just a schematic diagram, where you would have a container of water here, like an apple juice can or a juice container filled with water, and you might do something underneath here, like, I don't know, putting like you're taking a piece of cork and putting a pin in it and putting a cheesy or a peanut or something there like that, or having a candle, burning candle wax. I think that's the experiment they do, where they would burn the cheesy or burn the candle wax. So let's just change this to a candle. So what you're going to do is you're going to take a candle and burn underneath this tub of water, all right, that's on a ring stand. Okay, this is all going to be on a ring stand like this, and you're going to have your wick here. And in this tub with this can of water, you're going to have your thermometer. And what you're going to do here is you're going to measure the heat of combustion of wax. Candle wax. Okay? And what you're going to do is you're going to figure out the mass of the candle that was burned. So you're going to figure out the mass of the candle because you're going to get a mass of the wax before and the mass of the wax after you burn it. So what I'm going to do is I'm going to weigh the candle, and then I'm going to light it on fire, let it burn for a few minutes, and I'm going to extinguish the candle, and then I'm going to weigh it again to figure out the amount of wax that was combusted. Okay. We're also going to weigh the mass of the water inside the juice can, or apple juice can, or a soup can, or whatever it is you want to use, or something that can hold the water there. And what you're going to do is you're going to light this candle and let it burn. There we go, flickering embers of love with our little candle. And of course, the assumption is that the initial temperature of the water is going to be measured, and then the final temperature of the water is going to be measured when we extinguish the candle, assuming we're going to be stirring this with a glass rod of some kind or a stirring rod. And what we're going to assume then, that all of this heat that's coming off the candle is going into the water. Now there's a lot of assumptions going on here. This is even worse than the simple calorimetry we've done on the other pages, because not only is the heat going to go into the water, the water's going to warm up, obviously, but we have to take into account the fact that, sure, isn't the can going to warm up too? And what type of metal is the can made of? Is it aluminum? Is it tin? Is it iron? Is it, what's it made out of? And what is the mass of this actual juice can? So that's going to be absorbing some energy. And not only that, there's going to be energy that's going to escape out to the environment. So some of the heat that's coming from this candle is going to be going into heating the actual air outside the can. So this whole experiment would be flawed in the sense that if I wanted to figure out the Q of the system, sorry, the Q of the surroundings, I'd have to do a multiple number of measurements here, would I not? Because I'd have to know that it's going to be the mass times the specific heat for water. Let me just change this again. Okay, I'm down on a tangent here now. Q of the surroundings is going to be Q of the water plus Q of the can plus any energy that's lost that we'll never be able to calculate. See, there's going to be a great big source of error in our experiment here because a tremendous amount of energy is going to be lost. So our surroundings would have to be considered the water, the can, and all this energy is lost. Now in your core lab, we ignore the energy lost and we try to accommodate the amount of energy absorbed by the can, assuming the can was made out of aluminum. So what we'd have to do then is we'd also have to weigh the mass of the can, and we're going to assume that it's aluminum and get the heat capacity that way. So not a real good experiment to do. Of course, we couldn't do this with a styrofoam cup because the candle would actually burn the styrofoam cup and it wouldn't work well. So not an ideal experiment for the most part. The results you're going to get are going to be very, very, they're not going to be close to what we expect to get. Therefore, not a real good lab. But if you've seen a question like this showing up on the public exam, that's one of the things they're going to be asking. You know, how could we improve this experiment? Well, instead of having this great big open container system here, they could say, well, let's burn the wet candle wax in a bomb calorimeter where, you know, things are a little more controlled and we don't have to take that into account. All right? So we'd have to be able to measure the surroundings by the water and the can here. Anyways, there we go. All right. I'm going to stop there. If you want some more information on this, let me know, and I can drop you a line on the can calorimetry business there. And check with your online tutor. They can help you out too.